it's our verification monitor. And if you want to ensure your network works as you intended, you should be interested in our tool. Okay. Each network, as you know, is not self-sufficient. It is designed with some intentions. People look forward, while people construct a network, they look forward for a network that works as they intended. So the network should be compliant with some forwarding policies. It is rather informal, actually. So some examples of forwarding policies. No external flow should go to the mail server of your office. If your office has several departments, these departments should be separated. Any two hosts in the office should be connected, and so on. In practice, these policies are not always held. What are the reasons for this failure? First of all, it might be some software bugs and hardware failures, but in general, most of the times, the actual cause of your failure is wrong configuration, is a mistake in configuration of your network devices. Our tool is designed for you to help you verify that configurations of your network devices is actually correct. It means that configurations that the devices are configured in such a way that your network will work as you intended. A little bit further. From the one point of view, you have your network infrastructure, you have a topology, and actually configuration of your devices. Our tool need you to give us a topology and give us flow tables. The rules, how we want packets to be handled at each network devices. From another point of view, we have requirements of network behavior. They are usually informal. You have to formalize them and express them in our specification language. So we will get our model representation and specifications in a formal language, and our verification engine will check that your network and your policies are compliant, or your network is not compliant with your policies. So our engine will provide you a counterexample and some sensible information about what's wrong with your configurations. What about mathematical model? First of all, we think that each header is just a binary string of a given length, as is the number of ports at a switching device and the number of switch. The packet state is just a binary string of a given length, and while packet traverses through the network, it changes its state. For example, if a packet goes through the link, it changes the number of switch and the number of port where it is located. If a packet is routed inside of the switch, the switch is the same, port is changed, and maybe a header is changed. So you can express the whole behavior of your network with a one-to-operand relation, actually. For example, as host A sends a packet to host B, the packet will traverse 4 states, as you can see in the slide. Now about our formal language. Here is the actual specification that forbids cycles, state cycles. I'll try to explain it with an example, actually. So we have a packet in a state X that comes to our network from some ingress port. At some point it came to a state Y, and actually from this state it can get to a state Z. So if the latter two are the same, we have an actual cycle. Our policy prevents cycles. Now about our tool evaluation. There is an open topology of Stanford University backbone. It consists of about 19 megabytes of switch dumps and rotor configs. It consists of 16 rotors in a two-level fat-tree topology. When we translated it into an open flow-like rules, we get about 700,000 rules in about 15 tables. In the right half of the slide, you see the work of our tool in real time. It finished the analysis of this network in about 5 seconds. During the analysis, VERMONT builds initial model state. It takes about 3 seconds and checks some policies. For example, our verification shows that this network actually contains some packet cycles. It doesn't contain black holes, so the packets are not missed inside the network. Also, the administrators of this network supposed that there are no routes longer than 3 hops. That is quite reasonable because of two-level fat-tree topology. But this policy is actually violated. So our tool works and works fast, and as a result, we found some errors in given network. After we evaluated this rather large network, we understood that our tool is fast enough to provide interactive verification. Actually, we tried to remove and add the rules from Stanford topology consequently and in parallels. We write some faster algorithm, and as a result, we could remove and add about 700 of rules in about 100 milliseconds. So we tried to apply VERMONT to verification of dynamic network topology, dynamic network. We integrated into an open flow, and actually it is a scheme of VERMONT deployment. We write our own proxy server and connect it to the choke point between the controller and the number of switches. Proxy server intersects commands from the controller and message from the switches. While it intersects commands from the controller, it asks a verifier that it actually an independent server if the command is safe. Verifier checks. Verifier anticipates the results of the command application to the network and give its verdict. If the command is safe, the command goes to the switch, and if it is not, the command is actually blocked. Now I want to give you some higher view about the place of VERMONT and formal methods in software-defined networks. There are some options how to guarantee that your control plane works as you intended. First option is to apply formal methods to control applications directly, in a similar manner as this method applied to real programs. If you could verify your control application, you could guarantee that it works correctly in each topology and every time, ever. In practice, this might be a drawback because of lazy programmers who write their application correctly for a given topology only, so this method is not applicable. Next one is the controller application is a specialized language to write your control application. With such a language, you could, if you could express what you intended in such a language, your program is compiled and is correct by the definition. And actually, the third option is to verify the behavior of your control application and actually your controller with the tool like VERMONT. We think that it is the most flexible actually. There are some other tools that provide the same functionality. Most of them are developed in some universities in the United States. Our tool has the most powerful specification language, and so you can express some intricate intentions to a network actually, and it is an advantage in comparison to other tools. Actually, next, our tool has the full OpenFlow support. I mean that the other tools are not always able to mimic OpenFlow behavior. What about the speed? Our tool sometimes lag in the speed to another tools, but actually some of these tools, such as AP Verifier, solve a much simpler problem. For example, the authors of this tool suppose that packet headers never change during the packet traverse the network, and so on. So our current results and our nearest goals. We have already constructed a program tool that is able to construct an initial model in about 1 to 10 seconds for rather large networks. We are going to implement a slightly faster algorithm to improve time of model modification and make some improvements in the speed of verification engine. Currently, we already have an expressive language, and in our nearest future, we are going to improve the functionality with the contour example and provide a deeper integration to the controller. So VERMONT could be used as an observer of controller applications. It could interpret actually some commands of control application and guarantee safe behavior of their commands independently on a sequence of the commands they are inserted into the network. And the third option, we are going to use VERMONT to provide some advice functionality for application. For example, application could ask our verification tool if its intention is safe, and our verification tool could answer yes or no. So thank you. I'm going to answer questions.
My question is about the ability of this dynamic checking of the integration requirement. Haven't you thought, or maybe there is a mechanism automatically correcting of the situation when you're replacing one piece of integration with another? In this case, you must do it as a transaction, and all the middle operations are incorrect. Do you understand that?
Yes, I thought about it. So if you change a large part of your configuration, some middle steps in this change may lead to incorrect states. Yes, so actually you can verify all the sequences of these actions. In reality, actually, all changes are sequential. So if your controller, SDN controller, changed something in the network, it does it in some linearization. So we can check the only linearization and be sure that the whole change, the whole bunch of its small change is correct.
Why did you choose POTC for specification rules, not CTA or TCTA?
Actually, when we consider the language, we supposed that we need a Boolean formula to express some states. We need some predicates, some first-order logic to express relations between the state, and the third intention was to add transitive closure to easily express such policies as an reachability. So we choose this.
I have a couple of questions. First of all, why you tested your VERMONT on the Stanford topology? I have special requirements for the input data, and for example, can you make the same case for the experimental topologies in Genie projects or other like talked before? And the second question is how you depend on the open flow protocol. Let's imagine if sometimes SDN, maybe in some case, said no to the open flow, said that I'm not using this protocol. Is it a complex decision for you, and what should you do in this case? Thank you.
Okay. The first question. We use Stanford because its configurations were open sourced. If you have actually some other open source configurations or some other closed source configurations that we could see, welcome. So about the second question. We used OpenFlow because actually several years ago SDN was an OpenFlow, so we tried to implement our verification tool on the most widespread notion of SDN. But actually we can rewrite the proxy API and use our verification tool with some exotic protocols, for example, just some SSH streams or SMP and others.
Is there another question? Okay, we may hold applause until perhaps after you present your second paper, if that would be okay.
Yeah.
So Eugene's second paper that he is presenting today is titled On Quality of Service Management in Software-Defined Networks by Multipath Routing.
The second speech is about the quality of service management in software-defined networks with multipath routing by multipath routing. First of all, currently there are a lot of applications that imply some specialized requirements to the quality of network connections. These applications are not really exotic. For example, consider some video streaming. This application needs a certain bandwidth, an upper bounded delay and jitter. Actually, the number of these applications grows all the time. There are a lot of new applications in new areas, so that scope grows as well. And what about the networks? How do they countervail this sustainable growth? There is a popular point of view that we do not need any quality of service management. It is the only feasible way to beat this growth is actually to use faster switches, wider links, and so on. Actually, we think that this point of view is rather bad, because at least from the point of view of pure rationality. For example, each application works correctly while it has a certain amount of resources. A small remark, I understand that resources cannot always be comparable. They can have different importance, they can locate in different points of the network, and maybe different by their nature, actually. But I illustrate our idea with the figure at the slide. Consider some application. On the slide there is a graph with two graphics. The red one corresponds to the dependence between the critical number of resources for operation application to operate correctly. The purple one is the maximum amount of resources this application would actually gain. As you remember, the network operates correctly if each application gets at least the required amount of resources. So if the network has no quality of service management, we need each application can actually take a lot of resources, much more than it requires, and some applications would be suffocated actually. So the network should provide as much resources as to provide each application with a higher, to provide high accuracy of each application. We have actually a lot of resources that could be taken and shared, and network could still operate correctly. And actually we have an internal fragmentation of resources. As a result, we have a huge over-provisioning and low network utilization. What are our options? How can we surmount this problem? First option is to use a well-known approach and model of integrated services. So we can reserve some resources at each switch, at each network device, and provide each application with the amount of resources it requires. Actually, this option is hard to implement in real networks because it's scaled not very well. And actually, this approach does not solve the problem of internal resource fragmentation. Another approach is the model of differentiated services. In this approach, we can separate flows into some classes of service and provide some share of resources to each class at each device in the network. This approach is easy to implement, but as a result, we have limited and actually indirect control over the quality of service that application gains. So it doesn't actually solve the original problem. And roughly speaking, we can say that current model, these two models of QoS management, provide insufficient control facilities or or their implementation has an excessive cost. What about the causes of this failure? I think that the huge problem here is the decentralized state that actually separated among the devices on the network. So each device in the network should collect the global state and solve the problem of consistency and convergence. Actually, each device's network should solve the hard problem of resource shadowing. Well, SDN provides a centralized control. Unfortunately, SDN is not enough to solve all the problem. Next problem is how to get actual application requirements from the network. Possibly, SDN controller should provide some interface to anticipate the requirements of applications. And the next problem, even if we have a global state, it is really hard to schedule resources efficiently. It is a multi-constraint optimization problem actually. It is a hard problem to solve in the controller. Actually, we think that both of these problems could be solved with one approach. We can integrate some QoS management facilities into the host, into the end host of the system. This software agent located at the hosts are able to anticipate the requirements of actual application and anticipate the quality of service provided to their flows. And second, actually, these agents are able to reschedule the resource allocation. So we suppose each host in the network, at least some hosts in the network actually, has a pre-installed multipath routing agent. This agent provides an application with the usual traditional socket interface, so they do not see any difference between usual protocol stack and our protocol stack. Internally, our multipath routing agent creates a number of additional shadow sockets and actually distributes the flow, application flow among these sockets, among a bunch of independent subflows. Some data of original application flow goes inside of one network flow, one subflow, and other parts go inside of their own parts. As a receiver, our agent should multiplex these subflows into original application flow. What about other reliability of multipath routing agent? First, it estimates quality of service requirements and estimates their provided quality of service. Second, it tries to route subflows by a different path. I will explain this in more detail in the next slide. And next, it can react to violation of quality of service requirements by opening some new sockets or adding some new subflows, and react over provisioning by closing subflows and deleting some sockets. What about a different path? Actually, we can implement this idea with any modern controller. We suppose that each subflow carries some mark of a parent flow inside of its leading packet. It could be protocol options, or actually it could be a part of a packet body. Next, controller intercepts the leading packet of a subflow, match this mark. Match the mark of this packet with some of known flows, and take this information while constructing a route for this subflow. And actually, the controller can monitor the state of the network and identify congestion points, congestion network elements, and bypass them. And what about a simple network without different paths? Actually, we can see that our approach is compatible with the model of differentiated services. So we can use multiple subflows and require different classes of services for different subflows. So we have a flexible tool for resource handling along a single path either. Now some words about managing this construction from the controller. As we can see, controller has wide abilities to monitor and control actually the allocation of network resources. It could limit cumulative bandwidth of subflows. It could limit the number of subflows and the dynamic of the instantiation. And actually, if some flow violates the policy, controller can close some subflows or all subflows. In our model, the work of controller is similar to the work of arbiter that verifies the correctness of some predefined policies, quality of service policies. What about the efficiency of our method? Just a remark, quality of service method is good enough if it provides such an allocation of network resources as to meet all the requirements of an application and provide high utilization actually. So it is hard to formulate formally. What about existing methods? Integrated service model suggests us to search some static distribution allocation of resources. Differentiated services provide us with ability to search resources in dynamic but locally at each switching device. And what about our multipath routing? Actually, it has the largest search space, and in theory, it could be really efficient. So, I'm ready to answer your questions.
Am I right that you assume that the application shouldn't use the usual TCP socket but some specials?
Yes, you are correct. Our socket has a similar interface.
I see. So the next question is, consider another method of distributing the output of the TCP socket, like using the typical means of link aggregation and putting something on top of them. Because I know from real practice that to modify the application is the task. The magnitude of it is equal to implementing all this SDN with the controller stuff and buying the hardware, actually, if you're working with a real application.
As far as I get you right, the question is about should we rewrite the application to use our socket?
The question is why in your case you have chosen the approach when you suppose that the user rewrites the application, but not haven't concentrated on some method which works outside the application. So why you would suppose that rewriting the application is a practical approach in this case?
Why did you decide that? Why should we rewrite the application? I can get it. You shouldn't rewrite the application if you have a similar interface to the network stack.
So you need just to recompile to what?
We have an agent, broadly speaking, an agent inside of the operating system kernel. So your user application, user-level application doesn't see.
So it intercepts TCP. So.
Yes.
Oh, okay. This is the answer.
Okay.
So the idea was to split regions fully from set of server flows.
Yes.
So our question is how to assemble them back from server subsets in the proper order. Let's say the records all together from server subsets are flows.
Actually,
Ну, то есть мы потоки брали из потоков, а потоки была речь. Как их собрать, чтобы обратно правильные потоки собрались в правильном порядке.
Okay, the idea is to use the same approach actually as is used in multipath TCP. So this problem is already solved. The only difference is that we are instantiating new sockets, new internal sockets in dynamic.
Just one, I would like to add that it's not exactly like multipath TCP, because multipath TCP implementation just generates several sessions at the same time and then try to use it. We don't do this. We just every time try to estimate the bandwidth which you are accessible for you, and if this bandwidth is not enough for application which specify its requirements initially, we initiate the Eurobit. This way.
What algorithm do you use to find the best new route inside the topology?
Actually, the simplest algorithm is to identify the congested point at the network and exclude it from the topology while constructing a new route. So you have to apply the extra several times, for example, or you can use some more advanced algorithm with a faster dynamic of graph modifying. I'm sorry, I don't hear you.
The extra with some modifications or simple extra?
Actually, what is the difference? Okay. Thank you.
Nice meeting.
Thank you very much, Eugene.
Thank you.
Wi-Fi networks around us.